Hello, my name is Yerbat Hasanov. Today I will present you our paper on final level sequential Wi-Fi-based indoor localization. Localization task aims to determine user's position in space. It is essential component of various applications such as emergency response, healthcare, and public safety. Localization tasks can be categorized into two main subtypes: outdoor localization and indoor localization. The outdoor localization problem has been effectively handled using global navigation satellite systems such as GPS, GLONASS, and Galileo. On the other hand, the indoor localization remains an open problem. Indoor localization is the task of determining users' position inside buildings where satellite-based techniques are ineffective. Common approaches utilize Wi-Fi signals, infrared, Bluetooth, magnetic beacons, and so on. Among these, Wi-Fi-based solutions are the most convenient. Specifically, approaches using Wi-Fi received signal strengths are considered more practical because they don't require any additional hardware except existing wireless access points. Wi-Fi-based localization systems are usually developed in offline and online stages. During the offline stage, a radio map of a building is first constructed by recording Wi-Fi signals at different predefined reference points. The constructed map is then used to build localization system. During the online stage, the built localization system is used to determine users' position in real time. Most of the existing works focus on discrete indoor localization, where position is determined arbitrarily and independent from previously received RSS values. In those works, the Wi-Fi datasets are also constructed by statically recording RSS values one by one at grid-like layout. Such datasets are unsuitable for sequential indoor localization. To address this problem, continuously recorded Wi-Fi datasets have been presented. However, in these datasets, the intervals between consecutive reference points are large because position labeling is very challenging. Additionally, existing sequential indoor localization approaches have discrete outputs, which are not scalable to larger areas. In this work, we study final level sequential indoor localization using recurrent neural networks with regression output. The overall network architecture was jointly optimized fully end-to-end to minimize error propagation between different modules. In addition, we present our Wi-Fi dataset containing 290 trajectories of sequential stream of RSS values and corresponding positions recorded every 5 seconds. The Wi-Fi dataset was collected at 4th, 5th, and 6th floors of C4 building in the Nazarbayev University. To record final level Wi-Fi RSS and corresponding positions, we employed Aruka markers and computer vision techniques. Aruka marker size is 14 by 14 cm and they were generated by Aruka's original dictionary. In total, 654 Aruka markers were placed on ceilings and walls throughout the 4th, 5th, and 6th floors of C4 building. Aruka marker positions were determined using total station Leica TS06+. Finally, Wi-Fi RSS and corresponding positions were recorded by carrying laptop with internal Wi-Fi module and external web camera. Wi-Fi module was used to scan and record Wi-Fi RSS values from surrounding WAPs every 5 seconds. Web camera was used to detect Aruka markers placed on ceilings and walls. A person was moving naturally at self-selected speed. We first recorded the training set trajectories. These trajectories are identical, recorded in both directions, and are not allowed to cross floors. To reduce the effects of noise and fluctuations, we collected them at different days and times of the day. Next, we recorded the validation and test sets trajectories. These trajectories are manually created to imitate a realistic walking path, for example, from office to toilet or elevator. Unlike the training set trajectories, these trajectories are unique and have been manually checked. In total, we collected 290 trajectories, and they were split as follows: 120 for training, 85 for validation, and 85 for test sets. Note that our Wi-Fi dataset is much larger than previously reported sequential datasets. For example, the total length of our dataset is around 42 kilometers, and the total duration of our dataset is around 42 hours. In the training set, 436 distinct WAPs were identified by their MAC addresses, Here you can see the histogram of the number of WAPs detected for each sample. Now let me describe the experiment setup. So all the experiments were conducted on our Wi-Fi dataset. For data preprocessing, we did the following steps. First, we removed all the WAPs detected less than 5,000 times. Next, RSS values of undetected WAPs were set to -100. We evaluated two feature representations, which are raw and PAUD. In raw representation, the original RSS values are kept unchanged. On the other hand, the PAUD representations are computed using this formula, where Ri is the RSS value corresponding to i's WAP, and beta and C are hyperparameters set to mathematical constant E and -100 respectively. As evaluation metric, we used mean error distance computed using this formula. Here, this is Euclidean distance between i's reference positions and predicted positions, and n is the total number of samples. Since our evaluation sets consist of several trajectories, the mean error distance was computed over all trajectories combined together. In our experiments, all models were trained on the training set, the hyperparameters were tuned on the validation set, and the final models were evaluated on the test set. First, we evaluated non-sequential baseline systems based on conventional techniques such as linear regression, decision trees, and k-nearest neighbors. Here, the best results are achieved by KNN using PAUD feature representations, which is around 3.83 meters. Next, we evaluated non-sequential baseline systems based on feed-forward neural networks. Here, we used PAUD feature representations, and we tried different number of hidden layers. And the best result is around 3.25 meters, which is around 15% relative improvement over best KNN model. The hyperparameters of FNN are listed here. Finally, we evaluated sequential systems based on recurrent neural networks. Here, we also used PAUD feature representation, and for fair comparison, we constrain our model to have single recurrent layer and to have less number of parameters than in feed-forward neural networks. The best result is around 3.05 meters, which is 6% relative improvement over feed-forward neural network-based models. The hyperparameters of RNN model are given here. Now, let's see some test trajectory example with ground truth and predicted samples using KNN model. Here, green points are ground truth positions and red stars are predicted positions. We can see that predicted samples are inaccurate and abrupt. In addition, the intervals between consecutive predicted samples are irregular. This is the same example, but positions are predicted using feed-forward neural network-based models. Here we can see that predicted samples are inaccurate, but they are better than in KNN case. In addition, the intervals between consecutive predicted samples are still irregular. This is the example with positions predicted using recurrent neural network-based models. Here we can see that predicted samples are more accurate and smoother, and the intervals between predicted samples are quite uniform, except the beginning of trajectory where our RNN model has insufficient information. In this work, we have demonstrated that final level sequential indoor localization performs better than non-sequential models under same conditions. We also present efficient approach for realistic and final level sequential data collection using computer vision techniques. By using that approach, we collected a large-scale sequential dataset recorded over multiple floors every 5 seconds. We named that dataset Wi-Fi and made it publicly available to advance research in this direction. For the future work, we plan to collect other data types from different sensors such as magnetometer and inertial measurement units and investigate the sensor fusion techniques for finer level sequential indoor localization.